Hi, this is Kan-Lin Hsueh speaking. In this section, I'm going to introduce the classification of fuel cell. There's many types of fuel cell, and the material used in those fuel cells are different, and there will be cause their operation temperature will be different. And because those different type of fuel cell, the operation condition or the temperature different, maybe cause they might end with a different kind of application. So this, the first we're going to introduce how many different type of fuel cell available in so far in the literature or the web. You can see there's all different kind of fuel cell available or under development. So for instance, like a DMSC, direct messenger fuel cell, PNFC, proton exchange membrane fuel cell, PAFC, phosphoric acid fuel cell, and so on. All this type of fuel cell you might think a majority of the fuel cell was classified by what type of electrolyte they've been used. That means the electrolyte is the material, ionic conducting material, which is separate the anode and the cathode. It's a conductive, but it's only conducting the ion, not electron. So there won't be shortage between the anode and the cathode. For instance, for the proton exchange membrane fuel cell, the electrolyte actually the solid polymer. The polymer have the function to proton exchange, can transport the proton. So we call the proton exchange membrane fuel cell. If the electrolyte is a polymer, porous polymer, and saturated with phosphoric acid, then we call this type of fuel cell is a phosphoric acid fuel cell. If the fuel cell, the electrolyte use the potassium hydroxide, it's an alkaline solution, then we call this fuel cell is an alkaline fuel cell, and so on, such as the molten carbonate fuel cell or solid oxide fuel cell. The solid oxide fuel cell uses the zirconium oxide as a major substrate for the electrolyte, so we call it a solid oxide fuel cell. The exception over here is a direct messenger fuel cell and then direct carbon fuel cell. The direct messenger fuel cell, the structure or the material used for the DMFC is similar to the PEN fuel cell. The only difference, as a major difference, is instead of feed the hydrogen as a fuel, it feed the methanol as a fuel. Because the methanol at the ambient temperature and then pressure is a liquid phase, is a liquid form, so it's much easier and safe to carry and for the portable application. Compared to the hydrogen, you have to use compressed air hydrogen cylinder, which is not convenient for portable application. And the direct carbon fuel cell, the fuel cell structure itself on the material is similar to MCFC or SOFC. In the literature, you can find that they might have the MCFC or SOFC structure, but the difference is that instead of feeding the hydrogen or methanol or the methane, is feed the carbon powder, very fine grind carbon powder, feed directly into those two type of fuel cell. We call it a direct carbon fuel cell. The last fuel cell is a microbial fuel cell. The microbial fuel cell use microbiome or the enzyme as the catalyst on the electrode. So, but the structure itself, so far we see, is somewhere very close to proton exchange membrane fuel cell. Inside, use the platinum as a catalyst. They put the microbiome material or the enzyme on the electrode. They decompose the glucose or the sugar, those chemical energy in there, and into the electricity. Before we the fuel cell, what the difference between the fuel cell, battery, and the solar cell? Over here, we give a brief statement over here. For the fuel cell, it's like electrochemical power generator. The fuel cell itself, the electrode in the fuel cell, is acting like a current collector or as the catalyst. The active material, like hydrogen, methane, or methanol, was fed from externally into the fuel cell. And in the fuel cell, the electrochemical reaction taking place inside the fuel cell and produce electricity and heat. The product, if you use the hydrogen as a fuel, the product will be the water. But if you use the methane or the methanol as a fuel, then maybe have carbon dioxide exhaust here. So this one is like a electrochemical power generator. As long as you had a fuel feed in continuously, it always will generate electricity and heat. For the battery, it's different. The battery, the active material like zinc or magnesium oxide was stored, is a part of the electrode. So the active material was stored in the electrode itself. And as long as it's being consumed due to the electrochemical reaction, then there's no energy output. So the electrochemical reaction will generate electricity and heat. If this reaction is not reversible, so we call it a primary battery. That means the battery used once, and then as long as the running all the active material was exhausted, then the battery the no more cannot produce electricity anymore, so it had to be recycled. Typical example like a dry cell or alkaline cell. The reason is that the electrochemical reaction is irreversible. You cannot reverse. Opposite to the primary battery, we call the secondary battery. Typical example like lead acid battery, lithium ion battery, or the flow battery. The major difference is electrochemical reaction in the secondary battery is reversible. So all the active material was stored on the electrode itself. So as it goes through electrochemical reaction, it releases electricity and heat. When all the active material exhausts, then the battery stop discharge the electricity. But since this is a reversible reaction, so you can charge the battery if just feed in the electricity externally and make this reaction reverse and then become original reactants, then the battery start ready to discharge again. And the solar cell, or we call the photovoltaic, is like is a part of, in my thinking, it's an electrochemical conversion device, but is physically convert the photo energy, the light photo energy shines through the photovoltaic, the PN junction, P-type semiconductor, the junction between the P-type semiconductor and N-type semiconductor. It's like a battery. You had a positive electron and a negative electron, and the physical phenomena and generate electricity. The fuel cell actually acting just like an electrochemical power generator. So the flow battery is similar to the fuel cell. The active material actually stored outside the battery. However, it's not, the flow battery is not like a fuel cell. It can be discharged because the active material is a strong acid or alkaline solution, so you cannot just dump into the environment. It's circulated between the battery and then the external tank. So after all the active material was exhausted and you recharge the battery, then the active material produce the active material, then they can discharge again. So the flow battery is somewhere between the secondary battery and the fuel cell. Is some kind of magnet between these two different fuel cell and the secondary battery. 那在这个地方呢，燃料电池，我们这个地方它有各种不同燃料电池。那我们从它的输出功率跟它操作温度呢，大概这边讲一下。在这个地方呢，这个输出功率来讲的话呢，我们这边有1瓦、10瓦、100瓦、1000瓦这样子。这1瓦、10瓦左右呢，这好像就是一般的电子产品，比如说手机、notebook 这些笔电这些呢，那它的需要功率大概在这里。也许像笔电，那如果说有硬碟这些东西的话，也许它在启动或者说关闭的时候，它可能需要比较大的功率，但是在待机的时候，它可能在这个地方或 DVD player 这些东西。然后呢，在脚踏车助动车的话，像这种可能是在100瓦左右，但是到摩托车或者是这些的话，可能就在1000瓦左右这个 range 里面。热电共生大概在1000瓦左右，就是一般的家庭用的那个一般家庭需要的用电，差不多在这里。不算冷气机的话，大概它需要的电力大概在1000瓦左右。到10瓦到10千瓦到100千瓦左右，这个 range 里面呢，可能大概就是电动车、电动摩托车它的一些操作范围。到巴士的话，大概是200千瓦左右。到 megawatt 的话，就等于一个小型的社区或一个校区、学校呢，大概它的用电量。那真正发电的话，一个发电厂大概在 gigawatt， 就1000个 megawatt 左右。那现在风力机呢，差不多一个风力机大概是2个 megawatt 到4个 megawatt 左右，风力机差在这里这样子。那个一个太阳光电板的话，1平方公尺的话，它大概发电量大概在100瓦到1000瓦左右，在这个 range 里面看它所用的那个能源转换效率这样子。所以在这里面呢，这个大概呢，这个燃料电池呢，它目前在文献上看到它的操作范围大概在这里，所以直接假设燃料电池它的发展主要是以携带型的电源为主，所以它实际上呢，它大概的所发展的 range 呢，大概在这里。那 PEN 的系统呢，它发展的比较成熟一点，有的甚至说试着用在携带型，但是它主要发展主力是在那个电动车这半或分散式发电、备用电力这一块，所以它的功率呢，大概是在这个 range 里面。那 SOC 呢，它本身来讲主要是用在定制型，就像小型的发电机这种了，所以它大概呢，它主要的发电呢，大概在100千瓦到 megawatt 等级这个地方。但是有些地方呢，实际上在研讨会上有看到，他们在携带型，他们的确有做在携带型的这个 range 里面，所以我把它画到这里面。实际上它真正适用范围其实是比较适合在这里，为什么呢？因为它的操作温度。我们就看它的操作温度，这个各种不同的电池呢，它那个操作温度会不一样，这就影响到它的这个应用所以说这个大概是 portable， 大概是在这个 range 里面。那各种交通运输工具，它的操作范围在这里。那定制型发电呢，大概是在这里面。那这个地方就说这些呢，像 SOC 它的温度就非常高，所以它不太适合说用在携带型，但是的确在研讨会里面有看到一些他们在携带型用的，它等于是用那个火锅用的那个瓦斯罐那作为它的那个燃料来源。那像火锅那个瓦斯呢，那个燃烧器呢，作为它的那个加温的设备用这种方式。那这种各种电池的操作温度呢，大概我可以给它归纳在这个地方。在这个 SOC 的话呢，它最早的话大概在1000度，因为它是用氧化锆作为它的电解质，那所以这个来讲，在非常高温下它才能够传导离子，所以这个来讲它操作温度非常高。但这么高温度呢，其实它的应用来讲，其实使用的材料其实不太好找到，所以说呢近来慢慢的一些随着科技发展呢，它的操作温度呢可以慢慢降低下来。它这里面就是在氧化锆里面增加一些其他的杂质，有点像半导体里面掺杂这种现象，提高它的导电度。这样子它的操作温度就会降下来，使得说它的应用范围也比较好应用，因为那些一些耐高温的材料也比较容易找得到。那 MCFC 呢，因为熔融碳酸盐类呢，它操作在这个范围里面。 那直接碳燃料电池呢，它实际上就是 MCFC 或 SOFC 的那个变形，只不过是它用碳粉进去而已，所以它的操作弯度范围呢，其实差不多跟 SOC 或 MCFC 差不多。那磷酸燃料电池呢，它的是用纯的磷酸，所以它跟水的平衡操作温度呢，差在200度左右。所以这个时候呢，它的操作温度大概在200度左右，在这个 range 里面。那 AFC 呢，碱性燃料电池呢，它的操作温度其实要看里面的 KOH 是用接近水溶液的话，它操作温度比较低。如果是用几乎是纯的 KOH 的话，它是熔融钛的话呢，它的操作温度就会比较高。那 PNFC 呢，它目前来讲是质子交换膜燃料电池，是用 Nephium 做这个它的 membrane， 它的操作温度大概是60度到80度左右。但是呢，现在有希望说呢，有一些发展的，希望说把它的操作温度把它拉高到接近到 PEN 的系统，这个 PAFC 的系统，这样子的话呢，它对一氧化碳的容忍度或是它的操作水热管理就变得非常的简单。它就是要把这个现在所谓的 Nephium 这个隔离膜呢，转换变成耐高温的质子交换膜，比如说像是 PBI 这些其他的一些或是 SPEK 这些东西呢，它的操作温这些高分子膜呢，它耐温度比较高，这样子。那直接甲醇燃料电池，因为它本身来讲就是用在3C 产品，而且甲醇呢，它的沸点在30几度，所以它的操作温度其实大概都在30几度、40度左右。因为燃料电池它操作的时候可能会产生一些热，所以它实际上是在室温下面，但真正操作的时候可能会在30度、40度左右。但的确在文献上有人试的时候把它操作在100度，就是用甲醇的蒸汽送进去这样子。但大部分在3C 产品都是在大概在室温左右。那个微生物燃料电池或生化燃料电池的话，就像微生物这些东西或酵素，它绝对不可能操作在太高温，所以它大概都在30几度，操作在这个温度下是它比较好的操作温度范围。就是由于这些温度操作范围和它的一些特性呢，像这些是属于低温型的燃料电池，那大概呢，它比较适合用于说，比如说3C 产品或是交通工具，常常要开关的这种东西。那在高温型的话呢，它比较适合在定制型的发电这种东西或分散式的发电，在这里面，目前来讲是以这些为主力。目前来讲的话呢，目前比较接近商用化的话呢，大概是 MCFC、SOC、DMFC 跟 PNFC。那 MFC 呢，这个呢，它现在还是在非常初期的研发状态，因为它功率非常的低。FC 的话，因为在地表的应用来讲，其实它是最早是用在太空中，但是呢，因为在地表上的应用来讲有二氧化碳，这二氧化碳会造成它电池中毒，所以说它这个现在慢慢在比较没有在实际的应用这样子。那 PFC 的话，磷酸燃料电池，它其实最早它是最先商业化的这个磷酸燃料电池，全世界曾经有过400-500座200 kW 的这个发电系统，但是呢，当这 PNFC 发展成熟的时候，它所有的市场全部被 PNFC 取代了。is a phosphoric acid, is a PN fuel cell, solid oxide fuel cell, SOFC, and the DMSC is a close to commercialized, especially a PN fuel cell and solid oxide fuel cell. The fuel cell was developed a long time ago, maybe 200 years ago, but first application somewhere around 1950 to 60, the power for space vehicle. Then it's a start developed for the stationary power or for the power for the electric vehicle. And in the 1990s, the cell phone notebook start develop, so the fuel cell also try to migrate and try to develop for the portable application. All this is still in the infant time until somewhere in the I will say 2010, somewhere in that case, start get commercialized like stationary power or electric vehicle. Somewhere in recent year, this year, getting close to commercialized mass production. But the portables didn't see too much yet. It still take quite a while. The fuel cell in Taiwan, you may think they started in the earlier somewhere in 1987. Start at the E3, the Green Energy and Environment Research Laboratory. At that time, they focused on the PFC, fast acid fuel cell for distributed power generation. And in the year 2000, they switched to PNFC and then start development since then. For solid oxide fuel cell, the Institute of Nuclear Energy Research, they focus on solid oxide development. And then the E3, MCL, Material and Chemical Research Laboratory, they are focused on direct messenger fuel cell. There's a different kind of electrochemical energy conversion devices, and so far the operation power range somewhere I show on this diagram. The fuel cell somewhere from the 1 watt all the way to megawatt, depends on use for portable, transportation, or distributed power. The portable maybe I should draw on somewhere 100 instead of 1 kilowatt is too much. And for the solar cell, for the portable application, it might be in a very low range, all the way to the solar farm, and for the renewable power generation to the megawatt range. And then battery also for the portable application, all the way to the energy storage for renewable energy, somewhere around here. As a reference, a typical wind turbine right now used somewhere is around the 1 megawatt range, maybe 2 megawatt to 4 megawatt. For the photovoltaic, 1 square meter is somewhere around 1 kilowatt. But if you really consider exactly the power generated, somewhere around 200 watt per meter square, in that range. And for the nuclear power plant is somewhere around this range, gigawatt range, you may 2 or 4 gigawatt, that range. For the redox flow battery, the purpose for this the development is for the as an energy management for power grid, or in couple with renewable energy such as photovoltaic or solar cell. So their power range somewhere around this range, from kilowatt all the way to megawatt range, because the energy density for those batteries is very low. So it's not going to be used for the lower power range, such as for portable, even for transportation. This one only used for stationary energy storage purpose. For biofuel cell, so far the power range is very low. It's more suitable for biosensor rather than for power generation. But for the long-term goal for the biofuel cell is it will be incorporated with biomass. So you might think this is third generation bioenergy. They'll convert the garbage, whatever, or recycle all the waste directly into electricity, and also serve as a wastewater treatment. They'll convert all the organic into carbon dioxide in the long run. It will be can be classified as a bioenergy technology rather than for fuel cell technology, maybe in that sense. So over here, for the fuel cell application, in the previous section we've been mentioned there's the fuel cell application, and in this section we tell you about the type of fuel cell. There's so many types of fuel cell available or under development. And in this section we talk about the fuel cell type of fuel cell classification of fuel cell. In next section we're going to talk about how the fuel cell looks like, a key component in the fuel cell.